Great, so what we have now is essentially this little query that we've got, and now we want to start looking at, see if it's what will make sure that we're in equilibrium. So essentially, let's start off by looking at, there's a force acting, there's a stress acting here, and if I multiply that stress essentially by the area, so I'm going to take the area as dy in this case, and I'm going to multiply it then with a unit dz. So what's going to be implied here the whole time is that there's a dz, which I'm just going to make 1 for now so that we don't have to drag it along, because I want to focus now on this 2D sort of setup. So essentially what we have is for sum of forces in the x direction is then negative sigma xx, because that sigma xx is acting in the, if I multiply it now with that area, it's going to act in the negative direction. So sigma xx, and then I'm going to multiply with the area as dy, and then the 1 is going to be implied. So I'm going to just write the 1 there so that you can see that it's at least an area multiplied by sigma xx. Okay. What is going on? Oh, apologies. Okay. All right, so that is essentially what we have there. The next aspect that we have is at here, we sit with tau yx, and this tau yx, if you look at the direction, it's acting in this direction, so I have to multiply it essentially with this area again with the unit vector, so that's at least a positive one, so that's positive tau yx, and then essentially what we know is that there's the variation of tau yx with respect to y, so that is essentially the tau yx that went up, that variation contribution that we have there. So this is the tau yx variation with y times dy, and this times dy is now because of that variation part that we have. All of this I have to multiply now with the correct area. So hopefully I'm not going to run completely out of space, but essentially that area that this is acting on, this top here, is just dx multiplied by 1. So I'm going to write dx and 1. Okay, so that takes care of this edge and this edge of the cube. And if I look at now on this edge, what forces are acting, I see essentially I've got sigma xx plus the variation of sigma xx as I moved across. So that is that variation that I have to add there. So that is then essentially the variation of sigma xx as we moved in the x direction multiplied by dx. So that is what we have there. The area on which this acts, again, this face here, the area that we have here is distance dy times 1 for the unit in the z direction. And then we need to ask ourselves at the bottom, there's another shear component that's acting in the horizontal direction. It's acting in the negative. So this is essentially the same as that one. It's just in the negative direction. So I'm going to say negative tau yx. And at the bottom here, it's times dx times 1. That is the area over which that acts. So these are sum of forces in the x direction. That must be equal to 0. Okay. So let's first simplify a little bit and see what cancels out with what and what we're left with. So if you go through this process, essentially this negative sigma xx dy plus 1 will cancel with this positive, positive sigma xx times dy times 1. So I can say this will cancel with this, and what I'm left with is essentially this term multiplied by that, so that what I'm left with there is sigma xx partial x times dx times dy. Okay, so that is what I'm left with there. So that term is now gone. If I look essentially what's going on here, again there's a positive tau yx times dx times 1, and there's a negative tau yx times dx1. So this one and this one will cancel out with each other. And what I'm left with is essentially partial tau yx partial y dy dx. And that is essentially equal to 0. Okay, so that is what we get out. If I say that it's dx times dy and a dy dx, I can then rewrite it as sigma xx partial x plus partial tau y partial y. That gets multiplied then by this dx dy must be equals to 0. Okay, so to ensure that this is always the case, because I could maybe choose this dy dx can be chosen sort of arbitrarily. It should hold over sort of, in general, it doesn't matter what size I choose my little cube, I want this to always hold. And to ensure that, I can then just make sure that this term inside here, that gets multiplied by this, because this dx times dy is definitely not 0. It's some small values maybe, but they're not 0. And to get this term to be equal to 0, this must then be equal to 0. So this is essentially what we resolved for sum of forces in the x direction. So that's what we get out. Okay, so what is important about this is, what it's saying to us is, if there's a variation in x stress over a body, if the x stress varies over the body, there must be a corresponding shear to counter that. This is what it was. Otherwise, we cannot have x equilibrium. Okay, so this is important for consideration, because if you consider, for instance, the case, I'm just going to give you an example here, just as a thought experiment, not going through the mathematics and algebra, but I just want to give you a thought experiment. If I go through the example here of saying, here's a bar that I pull on, a uniform bar that I pull on, that stress in that bar is constant, okay? And so there's not going to be any shear related to that. But what happens if I have a tapered bar? Let's write it with the boundary condition properly. If I have a tapered bar, okay, it doesn't have to be that, but maybe it's a little bit crazily tapered. But if I've got some bar that is obviously the area is not uniform, okay, it's some linear variation in the area. Essentially, and I still apply load there. What I learned from this is that if I were to take a cut here, that surface area of P would act over a smaller surface area than if I take a cut here, okay? So the stress here would be higher and the stress here would be lower, just because of the fact that the body is tapering. But what it's saying to me is, if I were to model this in a 1D case, okay, and I have a stress variation, so the stress is varying from being low here towards higher as I go to the right. There's a stress variation. There has to be a corresponding shear to be able to count it. But if I do a 1D sort of model of this as a bar, I only have this component. And so when we simplify a thing like this, for instance, from a three-dimensional kind of stress state, and say, let's just only worry about things to vary in the one direction. So we try to simplify it as a 1D stress model in the one dimension. We cannot actually get an equilibrium equation to resolve for this. So the fact is what we also learn from this is, because there's an area variation, is in real life there will be associated shear to counter essentially the fact that I've got that body here. The stress varied in the x direction from this side to this side. There was now stress variation. Then there has to be a corresponding shear that counters for that. So that is just important. So that is non-negotiable, and that is that's the way it is. Okay, so that's what we learned from that. Sum of forces in the x direction. Okay, we can complete the process and say sum of forces again in the y direction, and you can go through this and confirm it for yourself. But essentially what we get out then is that we sit with a what did I write here? Apologies, I wanted to say, I see this is wrong. Essentially I see a variation of this shear with respect to x plus the normal is equal to 0. And that is what we'll get for the sum of forces in the y direction. And this gives us that relation essentially. And in 3 dimensions, there's just what happens is that there's additional term to say that there's now a tau associated with z and x, with how it varies with respect to z, that gets added. So there's then 3 terms in the 3-dimensional case, as opposed to the 2 terms in the 2D case. But hopefully this will give you a clear understanding of where those equations in the textbook comes from.